Howdy, y'all. I'm Professor Parks, PhD, and I make content on astronomy, science, skepticism, and mental health. Welcome to the channel. I'm hoping that I'm actually live because it doesn't look like I'm live on the tubes. Let's see. I am. Oops. Let me try this again. There we go. So let me try that again. Howdy, y'all. I am Professor Parks, PhD, and I make content on astronomy, science, skepticism, and mental health. And so I am going to, and the reason why I am live today, I want that to go away. And I don't like looking at myself, so I'm going to minimize that. Excuse me. Now, the reason why I'm going live today is that I was doing some science today. I was looking over some observations that I've taken during my trip to Indianapolis for the solar eclipse. This is tied into a larger effort to try to take data on the sun every day that is clear. I was able to do it today. I actually posted that on the data on that, or some images of that, on the communities tab. So if you have not checked that out, check those out. There's a big old sunspot group in the lower right hand quadrant. I was able to capture that, and so I took 3 images, one of the entire surface of the sun. I zoomed in a little bit. It's about half the sun, half the surface of the sun, and then zoomed in again on that sunspot group. And I hope to make a tradition of that, or rather a habit of that, so that whenever I take images and there's something cool to be seen, I'm going to just update you on what the sun looks like right now. Yeah, so I was looking at the data. And I was like, hey, why don't I go live and basically just give an update on how it's going? And so here we are. Just a recap for those of you who aren't aware of what I'm doing is that I recently was able to purchase a ZWO C-Star S50 using Patreon money. Due to the kindness of my Patreons, I was able to purchase this small scope, which is a fantastic little instrument. It's about $600, give or take. I really should look that up. It's either 5 or 6. I can never remember which. It's about $500 or $600. It's basically a desktop kind of thing, but it is fantastic when it comes to astrophotography, of taking data pretty much immediately from the sky, or taking data. I don't know what's wrong with you today. Taking data of the sky pretty much directly out of the box. It uses an app to operate. Unlike its bigger cousin, the EV scope, that allows multiple people to log on to the telescope in order to see what's going on. The C-Star, you're it. Essentially, it only allows for one operator and one observer. But honestly, I don't really care about that, because this thing is awesome, particularly because I can set it up and take data on the sun and then shut it down in about 5 minutes. So I'm in, I'm out. So it's very easy for me in terms of my scheduling. So if I'm walking to campus or what have you, I can go to class, come out, I can take it out, set it up, bing, bang, boom, hit the sun, and then go out and back to my office. So I have taken a considerable amount of data. I have data spanning, well, let me show you actually. And yes, I know I'm going to just wow you with an Excel spreadsheet. I know. You can't barely contain yourselves with the idea of checking out an Excel spreadsheet. I mean, I gotta say, Excel spreadsheets are just, they're sexy. So you've been warned, behave yourselves, that Whoops. I can, what is going on here? Apparently it's so sexy that StreamYards won't even let me show you my uh, spreadsheet. Let me try this again. ODS, share screen. Okay. About now. Nope. Still nothing. All right. How about this? Share screen, entire screen. How about that? We'll do that. Hey, there we go. Entire screen. As you'll be proud of me, I even put in colors and stuff to delineate what's going on. Yeah, I feel snazzy with this thing. All right, I gotta go over here. So yeah. All right, so let's start off. What is this spreadsheet? Actually, let's back off entirely and let you know what it is I am actually trying to investigate. Well, I am trying to investigate. This whole thing came out where one of my regulars, who is a science skeptic, Stephanie, she brought up something about distances to some. I'm not entirely certain what exactly was the inciting event, but it occurred to me I have this beautiful little instrument that allows me to take pretty nice images of the sun, and I'm like, I can extract data out of this. And so I was looking at this from both a science skeptic point of view and also from an educational point of view. Can I take data with this instrument over the course of a year to demonstrate certain things? Initially, what I wanted to demonstrate was to see whether or not I could detect whether or not the sun's apparent size changes over the course of a year. Our current understanding of science tells us that the Earth is an elliptical orbit with an eccentricity of 0.01 something, something, something. I don't know. I don't remember these values because I can Google. Slightly eccentric orbit. What that means is that the sun is going to change its apparent size by a certain fraction. Again, I haven't really looked into it. The number that sticks in my head is that the difference between our distance at periastron, close as we are to the sun, comparison to apastron, is about 3%. So the distance change between where we're closest and when we are furthest away, that's about 3% in terms of, kilometers and such. In terms of angular size, it's a little bit more. But anyway, I wanted to see whether or not I could actually demonstrate that. I wanted to see if I could take measurements and show that over the course of a year. Oh, and howdy, Charlie. And I thought to myself, this is a great project because, it came from me. But it's a great project because not only can it demonstrate whether or not it can demonstrate science. So I have this hypothesis that suggests that because of the Earth, if I make the assertion that the Earth is an elliptical orbit that is orbiting around the sun, that the implication is that the apparent size of the sun is going to change as a function of time as I orbit around the sun. Can I measure that? Now, at some point, I will be creating a prediction. I will be making a prediction of saying, all right, this is the expected amount of angular size change over the course of the year based on a model supplied by the computer program Stellarium. And then I will use this data to basically compare my observations to that model and see if they match. And if they match, then I have a pretty good case to state that yes, we are in fact in a elliptical orbit around the sun. The other thing that I can measure with this, and I will be measuring this pretty much every time, is I can measure the angular size of the sun. That kind of follows with it. kind of, wow, I am just all over the place today. Squirrel. Um, sorry. As part of this procedure, I'm going to be measuring the angular size in arc seconds, essentially fractions of a degree. And I'm measuring that angular size. A consequence of that, particularly when it comes to science skepticism, is that just due to simple geometry, that angular size measurement sets pretty much in stone the ratio between the linear size of the sun and its distance, and our distance to the sun. So while at the present moment, what I'm doing cannot absolutely tell me either the size or the distance to the sun in kilometers, I can fix that ratio. I can fix that ratio such that if you can come up with an independent means to determine one or the other, then you have the other. So if you assume for whatever reason, or you can figure out for whatever reason that the sun has an altitude of 3,000 kilometers, that then, coupled with my measurements, tells you exactly how big the sun is in absolute units. So, and I have, and so I've taken a lot of data. You can see here I've got data from March 14th. Each one of these entries, each one of these entries is in fact an image that I've taken. I also plan on making these publicly available so that if there are, so I'm doing my own analysis on it, and I will, as coherently as I can today, I will try to walk you through how I'm analyzing the data. But this is all very preliminary. I've really only been able to have time to sit down and do this for the last, I don't know, 2-3 days in total. So this is all very preliminary. Howdy, Blue. And I will point out where I think where the errors are originating. If there is going to be error put into this from a technique standpoint, then I will let you know where that is, and I will also ask for help from the what do you call that? The hive brain of the interwebs. But anyway, so I have these. So I plan on making these images available so that anyone can take the same data, analyze it in their own way, and test the results that I will put out. And so I've got quite a bit of data going on. So here is the indie data that I've been looking at. Then I've got some data from the 10th all the way down to 22nd of today. Happy Earth Day, by the way. Now, what is all this? What are all these sexy, sexy numbers? Well, just to tell you, this column is the latitude and longitude of rough latitude and longitude of the observations. Basically, I'm looking at this within, I haven't figured out exactly what my tolerance is, but it's going to be less than a kilometer because I'm not going to put down the absolute latitude and longitude for if I were to take it off, if I'm walking across campus. I'm pretty sure that the difference in the latitude and longitude from that position to where I usually take most of the data, which is right above my head, I really doubt that is going to make any sort of difference whatsoever. But ultimately, I will look into that because I want to make this process as transparent as possible. And I also want to make this, I want to basically dot all my I's and cross all my T's and all that kind of good stuff. But for right now, these are rough latitude and longitudes based on my position. And when we go to Indy, based on the Motor Speedway in Indianapolis. Because of the equations that I'm using, these are in degrees, and Excel, for whatever reason, hates degrees with a burning passion. And so I have to convert everything into radians, which is annoying, but I do it anyway. So you'll see here, some of these columns are degrees, some of these columns are radians. We got the local sidereal time. That is the time as basically dictated by the celestial sphere. For those of you who are not in the know, we have two ways of determining the length of a day. We have 24 hours, which is the solar day or synodic day, which is how long does it take, again, roughly, for the sun to go from the noon position all the way around back to the noon position. The sidereal day is the amount of time it takes for, say, the star Vega to go from the highest it is going to be in the night all the way around back to when it's in that same position, what we call the meridian, on a line which is drawn from zenith down to the south. That is the sidereal day, and that is 50 or 23 hours, 56 minutes in some odd seconds. So, again, I'll explain why I'm recording that. Right ascension and declination. These are the equatorial coordinates. Excuse me. These are the equatorial, the longitude and latitude coordinates of the sun at the time of the observation. And then these are the apparent latitude. These are the apparent altitude and azimuth where the sun actually appears in the sky relative to me on those days. Now, first admission. Obviously, right ascension declination, I'm pulling from stellarium. Altitude and azimuth. Now, if I were fancy like Dr. Bob, the science guy, I would pull out my own. Sextant and actually measure the altitude and azimuth, but I have not done that yet, as I do not own a sextant. I might be able to start measuring the azimuth now that I'm thinking about it using an app, but for right now, these two are taken from stellarium. If I can find a way to take those pieces of information or take those measurements myself, then I will do so in the future. And I will notate where I'm taking from stellarium and taking for myself, because ultimately I want to take as much data as I possibly can so that there is no accusations that I'm essentially proving the model effectively, where the model is giving me the data and I'm doing some analysis to basically show that that model is self-consistent, if that makes any sense whatsoever. I want this to essentially be used as, what's the word I'm looking for? A true test, as much of a true test as I possibly can. Eric, howdy. Use the radians function. I could, but I'll just multiply by pi and divide by 180. But like I said, it should just be I don't know, maybe there's a switch in here where you could just hit switch to degrees. Everything's in degrees, not radians. I don't know. Anyway, so what I'm recording from stellarium is the local sidereal time of the observation, the right ascension declination of the sun at that point, the altitude and azimuth of the sun at that point. These, again, azimuth I could probably get from an app. Altitude, to get this kind of precision, I would probably need a sextant. And so if someone wants to buy me a sextant, sure. All right. So I convert all that good stuff. Hope you all appreciate the sound effects. And let's talk about these columns right here. The reason why I'm doing all of this rigmarole is because of atmospheric refraction. One of the conflating variables that I need to take into account, because ultimately the backbone of all this, the real measurement that I'm taking to do any of this, is the apparent size of the sun. Now, again, modern science tells us that because we are encapsulated with a thick, relatively thick atmosphere, that atmosphere is going to act like a lens, because the index of refraction of that atmosphere is a function of height. And even if it weren't, it would still be different, because we would be going from the atmosphere to space and so forth. So what I'm ultimately rambling about is that we need to we need to take atmospheric refraction into account. Atmospheric refraction is going to potentially cause the size of the sun to change as a function of where it is in the atmosphere. And so what we're looking at here is a measure that astronomers use called air mass. We make one assumption with air mass, and that is the index of refraction, or the amount of atmospheric refraction that is occurring, is actual or azimuthally symmetric. So all we care about is how much of the atmosphere we're looking at as a function of height or altitude. So if you look straight up, you are looking through, by definition, one atmosphere. As you look down, as your angle of, as the altitude of the object drops, you are looking through more and more of the Earth's atmosphere. And so your air mass goes up. So air mass is a proxy for how much atmosphere you are looking through, and it increases with altitude. So what I wanted to do was, first thing that I need to be able to determine is our assertion is, again, that there is atmospheric refraction. That atmospheric refraction can affect the angular size of the sun. So I need to take that into account. I need to figure out what that relationship is. Now, if you haven't seen this for yourself, or you're doubting that this is the case, just check out images of a sunrise or sunset. You can see as the sun gets lower and lower on the horizon, and this is an extreme case, as the sun gets lower and lower on the horizon, the sun appears to be squashed, technical term, meaning that the apparent distance from pole to pole is shorter than the distance from the left side to the right side. I want to be able to not just determine whether or not I can see that effect, but I want to characterize it such that if I if I have, say, an air mass on specific days, say, for example, on the March 17th, I'm looking through 1.32 air mass. I want to be able to go to that relationship and have it tell me that if the sun is at 1.32 air mass, what correction do I need to make in order to eliminate any sort of interference or any sort of fuckery that the atmosphere is doing? In order to do that, I need to essentially map out what the sun is doing over the course of a day. Now, this all didn't occur to me until basically 2 weeks after I started this experiment. So I was sitting there on turn 4 at the solar eclipse in Indy, and I was like, wait a minute, I got time. I'm sitting here at, I think it was like 9 in the morning. Totality starts around 2 or so. I'm like, I got time. Let me see if I can sort of map this out. Now, again, preliminary. If I were to actually do this, if I were to actually to try to determine this relationship, what I would do is I would set up I think I'm going to set up on the parking deck right by this building. It has a very nice, clear, it has the best line of sight from horizon to horizon that I'm aware of, meaning that I can see the sun very low in the east and fairly low in the west. That gives me a large range over which to test any sort of function of angular size with air mass. And that way I can characterize it and so forth. Now, this also has to do with science skepticism, in that if we look at the globe model versus the flat earth model, and yes, for those of you who saw that I downloaded DIRTH's flat earth app, that was not a mistake. I have in fact done that because, well, apparently I have channel member money to burn, and so I decided to burn it. And so I have his app, and yes, I will be talking about that later. But if you assume that the Earth is flat and the sun is local and uh, local and small, then I know that there is no concrete model of the flat Earth. Like they always claim that we have no model, whatever. Well, I'm going to put this out there, and this has been put out there a number of times. So if there is a flat earther out there that disagrees with this characterization, please let me know. But but the way that we expect the sun to look as a function of time, if you're on a flat plane and the sun is orbiting around or moving around that flat plane at a fairly low altitude, is that we would expect the sun to begin to be very small when it first becomes visible, and then get larger as it gets closer to you. At the point where it's as high as it's ever going to be in your sky, it's going to be the largest it's ever going to be to you. And then as the sun moves away, the angular size is going to diminish simply because of perspective. So that I can also test in this same test to be able to characterize the angular size of the sun, the apparent angular size of the sun, as a function of air mass or position in the sky. I can also test this. I can see how big of an effect there is, because again, I haven't actually sat down and done the math to find out what that angular size change should be as a function of time, but I would expect it to be fairly dramatic. Now, this is what I found, again, all preliminary. So I have observations from, I have some kind of hair. Ah, there it is. I have observations from, I started at 9:31 in the morning. Now, every time I take an observation, I don't just take one image. I take 5 because of data statistics. Now, I take 5 because 5 is my favoriteest number. If I really wanted to be better about this, or if I wanted to have better error statistics, probably I would think taking 9 would be better. Well, taking a lot would be better. But the other thing is, the other point that I'm battling, or the other thing that I'm weighing on this, is that these observations need to be representative of a single, like a short period of time. So all of these observations, from 1617 or 617 to 621, within the error or within the precision of my measurements, I can treat these as being observations all taken at the same time. If I take more observations, then obviously time is going to progress, and that assumption, or that criteria, is going to fail. So, but going back to the main point, I take 5 observations, not just one. That way I can look at how the observations vary as a function of taking the observation. It gives me an idea of what can I expect in terms of error. If there's a large amount of slop, if I'm getting angular sizes that are, tens of arc seconds from one observation to the next observation to the next observation, then I know something is either wrong, or my device is not up to task, because I need precision way better than that. So 5 observations at every time interval, and I tried to do this every half hour ish. So I first started up, I was like, all right, 9:31, took some images. 9:34, I was like, all right, let me see what's going on. Getting better handle of what I was doing, or what my strategy was going to be. Took another 5 images. 10:28, another 5 images. 11:16, another 5 images. 11:55, and then finally at no, not finally, 11:55, 12:31, and finally at 1:14. That spans a range of altitudes, and I know this is all very exciting. Calm yourselves. This spans a range of altitudes from, and they're all on the one side of the sky. So from about 25 degrees to 57 degrees. Not a huge swath, not a very large swath, but it is significant. We're talking about what, 20 20 degrees across the sky. I would think that, at least for the flat Earth hypotheses, where the angular size is going to change as a function of perspective, I should be able to see that at some point. But again, I haven't done the math, so I can't say one way or the other. All I can do is report on the data. And so this is what I get. So, let me back up a second. Well, no, I've got it up here. So what I did, and I'll show you exactly how I did this in a sec, is I took all of those images and I measured essentially the diameter of the sun, top to bottom and left to right. So I have the blue is the width of the sun as a function of air mass or altitude. And then orange is a function of height as a function of air mass. And you can see that, and these, although not very well, for some reason I can't seem to get these larger, but I didn't really put a lot of effort into trying it. But I have done a simple a linear trend line to the data. Basically, I fit a linear function to the width, the blue data points, and I fit a linear function to the orange data points. And that's over here. And I know you can't really see this very well, but this R squared value, if the data fits perfectly, that R squared value is 1, effectively a quality of fit parameter. If it doesn't match at all, if it's completely random statistical noise, that R value is 0. Now, Tony, I don't know Excel well enough to say whether or not that is actually true. I think so. The problem that I have is that when I fit things with least squares, I include error bars, and I haven't included the error bars with these observations. So it's Excel least squares, and again, all very preliminary. I'm using this really as proof of concept. One of the things that I'm going to be doing eventually is, and yet another reason why I'm doing this is because I have let my coding skills atrophy to the point of effectively being non-existent at this point. I very much would like to change that. I really want to become fluent, or at least semi-fluent, in Python again. And because, I'm a geek and I think it would be cool to do that. And so I'm going to use this as a way to teach myself Python again. So when I do this rigorously, I will be writing Python code to effectively fit these parameters and so forth. But this is simply Excel. Don't forget about the Riley criterion. Yeah, I don't think we have to worry about that. I mean, my telescope, the CC is small, but I think her aperture is about 10 centimeters, but I actually haven't measured it. But I don't think we need to worry about the Riley criterion. I think the sun's big enough. So anyway, if you look at these two fits, what we can see is that, what I can see, what you can probably not see, is that the R squared value for the width is equal to 0.0301. That's essentially nothing. That fit is nonsense. It does not hold any sort of statistical weight whatsoever. For the height, it's a little better, but not much. The R squared value is 0.2678. These are not great fits to this data, but well, if we just qualitatively look at this, again, you can't really see it very well over here, but the scale, this is from 1 to 2.5. This is from 805. This is the number of pixels. So the widths are, for example, this data point, can't remember, the width is, this would be a width of around 807 or 807.5 and a height of roughly the same. My point here is that the difference in the y-axis is 5 pixels. 5 pixels. It's not huge. It's not huge in any stretch of the imagination. The plate scale tells me that I've already calculated, tells me that that is a difference in angular size of about 10 arc seconds. The sun is roughly 32 arc minutes in size. So this is a very small fraction of the overall size. This variance is a very small fraction of the overall size of the sun. So if I were to put on my science hat, what I would say is that we are not seeing any appreciable change in we do not see any change in the size of the sun as a function of air mass within the error of the observations. These are not statistically relevant trends. All we can see is that it effectively is they change within the error bars to each other. Again, one of the things that I'm going to do is I want to take the standard deviation of, say, these values, and to determine essentially the error bar for that value and move forward from there and actually do a proper least squares analysis to this. But I definitely wanted to show this because I think this is it's provocative in a sense, in that, again, only over a span of 20 degrees, I do not measure any appreciable change in the angular size of the sun in either height or width. So again, if we are looking at the sun on a flat Earth and we were doing perspective thingy-do, I would anticipate we would be able to see a change given the precision of what I've got. But yeah, I don't know. Howdy, my 2 cents. That's Dr. Mad Scientist to you, sir. I did not spend 8 years in grad school to be called Mr. Thank you very much. I don't know if you were referring to me or not. The sun is only half a degree in our field of view, pretty tiny. You could fit thousands of them on our sky. That's true. The sun is small, and it is roughly half a degree in size. You can. But the question is, again, what is the size of the sun as a function of distance? Now, from the globe perspective, I would expect that there should be some kind of trend here due to atmospheric refraction. From what I've laid out in terms of a flat Earth model, for lack of a better term, there definitely needs to be a trend there, because perspective tells us that the sun has to decrease with angular distance. And naively, I want to say that that's a linear function. The refraction is not expected to be linear. But I've tried better fits. I've tried exponential fits. I've tried logarithmic fits. Basically, none of them get better than this. That was directed at Crazy Tony. He's not Mr. Mad Scientist either. He's Dr. Mad Scientist. I don't know how long he spent in grad school, but I'm pretty sure it's probably less than me, but still a significant amount of time that he doesn't want to be called Mister. Anyway, so that's where I am now. So what I found is, oh, actually, I can do it this way. Hey, sheets. Ooh, sexy, sexy. I even use colors to point this out. Here, what I've done is I took an image of the Whirlpool Galaxy, and I completely ignored the fun part. I completely ignored the Whirlpool Galaxy part of it. And this was taken with CC. Ignore the Whirlpool Galaxy and just look at the stars in that field of view. And so I looked at about 11 stars, and this is basically the pixel position of each star and their right ascension and declination of each star. And effectively what I did was I determined the distance between star 1 and star 2 in pixel position, and then star 1 and star 2 in right ascension. So I have the distance in pixel position between 1 and 2 is here. The distance in angular size, or excuse me, angular distance from due to right ascension and declination of 1 with respect to the other. Here in radians, this gives it to me in arc seconds. I can then determine a pixel scale, meaning what this tells me, what this over here tells me, is that for every 2.3740, no, excuse me, for every pixel on that chip, that measures an angular size on the sky of 2.3740 arc seconds. And yes, that is in fact significant figures. And then you have, and that is the error bar in my plate scale, how I found the plate scale. Optical compression is an issue. I don't think we worship titles. I think that the issue for myself when I correct people that it's doctor rather than Mister is that I put a lot of work into it. I put a lot of work to get to where I am now, and I would appreciate if that work is well respected. Also, it gives you at least a baseline understanding of my level of expertise in the field of astronomy, and the same I would say goes for PhD Tony in the field of geophysics. Now, in terms of optical compression, again, I want this experiment to be as open and as fair as possible. So, my 2 cents, again, I will endeavor to put this data up and make it sometime soon on my website, profparksphd.net, so that anyone can download it, and anyone can analyze it. So if you have a way of dealing with or analyzing optical compression, then by all means, please analyze this data and let me know what you find, and I can compare it to you. You want me to address you as the king of what, Your Majesty? All right, so yes, so I have, again, returning back to this, I have a plate scale for my telescope telling me that for every pixel on my camera, every pixel in my image corresponds to to 2.37 arc seconds. So if we go back to here and we just do a kludgy sort of that times 2.37, that is, and then take that. Wham bam. So According to this, this is the width for this particular width value. If I apply the pixel scale, that tells me that that corresponds to an angular size of 1,917 arc seconds, which I divide by 60 and I get 31.95 arc minutes. Seems very well, that seems to fit very, very well for what I understanding. Again, I will also be going back with Stellarium and finding out what the globe prediction is for each of these on each of these days and times, and comparing and contrasting to see essentially how well I do. But yeah, so I'm at, it's a sanity check. Apparently I'm not insane, or at least not in relation to this. It seems like the methodology that I'm doing is working pretty well. So again, I will be posting updates on this as the methods become, as more data gets analyzed and as the methodology becomes a little bit more sophisticated. Now, let me talk about some of the stumbling blocks or some of the hurdles that I have to take into account. Let me share with you. Nope, that's not what I wanted. Hold on. La, la, la. So for reasons that I don't quite grasp, but it is what it is. I hate that phrase, but I can keep saying it for some reason. Is share screen. Yeah, let's share that back. Go over here. There we go. Okay. So if I were to take observations of night sky objects, like the Whirlpool Galaxy, for example, like what I'm planning on doing tonight, I can get those images. I can download immediately those images in a FITS format. Now, what that means is it's a flexible something system. FITS is basically a standardized way for data to be collected astronomically. Astronomers got together and basically figured out, all right, we got these new things called CCD cameras. Everyone's CCD camera is going to be a little bit different from everyone else's. How do we standardize these images so that we can compare apples to apples? I can compare my apples to your apples. So they came up with this FITS format. And that's what I'm used to dealing with. It's a really cool format. It has a lot of easily accessible metadata in it. But for whatever reason, for solar observing, all I can get are JPEGs. But which I think limits things for a bit. But I'm still using a program called Astro Image J, which is a free program. You can download it. You can install it on any operating system that you have, Windows, Mac, or Linux. And any flavor of Linux, it works there as well. The learning curve is kind of steep, but it is, in my opinion, a rather powerful program for analyzing data and visualizing data. So I decided, and initially, my first few attempts, I was like, I'll use GIMP. But I'm like, no, let me see if Astro Image J can do this, can handle taking data on JPEGs. And lo and behold, yes, it can. Now, here's the problem that I have. Oh, and I'll show it to you. Here's the problem that I have is, how do I measure the size of this thing with any sort of accuracy whatsoever, or more importantly, any sort of precision accurately? Now, I can tell you how I would want to do this. How I would want to do it is, does the university have central heating? What would make you ask that question? with give maybe the hat. I don't know. Yes, we do have central heating, but as anyone in U.S. academia will know, is that the heating and cooling of university buildings is usually the exact opposite of what you want it to actually be. So how do I do this? All right, so I can tell you how I would want to do this, but this would require a bit of sophistication, not only in terms of programming, but also in terms of, I think, analysis. Is that what I would want? Is I would want to load this into the computer. I would want want to write a code which read out what all of these pixel values were, very much like what this does, and I would set a fiducial point. I would set some kind of benchmark saying that if the pixel brightness goes from one side to the other across this across this value, and it drops below this data point or this particular value, then that is the edge of the sun. So, for example, I don't know if I have. I don't. So, say for instance, this over here. It's right up there. Look at these values up here. So this is like 123, and then it drops down to like 20. I would pick a value that I would claim is the limb of the sun, and then I would write a code that would analyze this thing and basically draw a line at that position where the brightness drops from bright to dark. But I can't do that. So at the moment, not to say that I couldn't do it, but I can't at the moment. So I'm left with doing the kludgy bit. So what I do is I'm zooming in so that I can see as much of the sun as I possibly can but still seeing the limb, the edge. Come over here and I take this tool, which is an oval shape selector. Come over here and I put this in and I match this up as best I possibly can, so that this orange ring, this oval, is the best approximation or the best determination I can make of the size of where the sun is. I then go over to here. I then click Analyze, Measure, and wham bam, I get this. What this is right over here, and obviously I wasn't overly careful, but what this width and height are is essentially it tells me, given this shape, what is the rectangle that shape would be bound within. And so the height of that rectangle would be 804 pixels. The width of that rectangle would be 108. So I'm using that as the width of the sun in this image is 108 pixels. The height of the sun in this image is 804. Again, this is illustrative. This is not the data that I've taken. You can see up here the data that I've actually taken up here, but it's within what I would term to be the error bars of my observations. Again, if someone could let me know a better way of doing this, a way that I could potentially implement other than, by eye, then I would be all for it. But right now, the best I can come up with is doing it by eye, doing it this way, and then going from there. But I freely admit there are other ways. I'm sure there are other ways of doing this that are more accurate. So we got that. What else did I want to say? Yeah, I think that's basically it. That was how I'm measuring things. All right. Actually, while I have you all here, one of the things that I want, and then I thought about, the more I do this, the more I'm looking at this data, the more I'm trying to tease out how much, and this is a game that astronomers and scientists love to play, is, all right, I've got this data. I collected this data for this particular purpose. But is there anything more I can say about the sun or things related to the sun using this data set? And it occurred to me, well, what about these sunspots that are hanging out here? Well, interestingly enough, let's put you over here. Nope, that's not what I want. I want that. I want that. I want that. All right. So obviously I've got all of this data. And again, this is on April 8th. We can see very clearly that there's at least 4 sunspots on here, probably 5, and almost definitely, probably definitely more, but on the order of a half dozen of spots. So what science tells us is that the spots will, one, change in number and location as a function of time, but also they will change as a function of location and number as a function of the solar activity, but also they will change in location based on the rotation of the sun. So we should be able to see these spots moving from one day to the next. Now, there's a wrinkle. I haven't really looked into this, so this is you and me. We're on basically on the same page here. Let's take the 16th. Let's just take a random image from the 16th and plop it down right here. What do we got? All right. Woo! Lots of spots. We have lots and lots of spots. All right. Okay, great. So science, our current understanding tells us that the sun rotates on average around 27, once every 27 days. Should be able to track that, right? If we have, so if I go over here and I take another random image, oops, that's not what I wanted to do. You can go away. You can go over here. And I come over here and I drop that down. Oops. All right, let's zoom in. That's 53.1, 53.1. Okay. So these are taken, and of course I have completely forgotten. This is from the 18th. This is from the 16th. So April 16th, April 18th. Doesn't look like there's a whole lot of, really can't identify what's where, which I kind of expected to be a problem. Someone could probably do math real quick and basically tell me how much of in 2 days, 2 out of 27 is what? How much as a percentage of the sun has it moved in that way? Yeah, that's not what I wanted to do. No, that's not what I wanted. There we go. There we go. Whee! Oh. All right. 53.1. This is the 20th. Hey, all right. Now we have something to kind of hang our hats on. 7%. Thank you. We have something to kind of hang our hats on. So here we have the 18th is on the right. The 20th is on the left. So the sun is presumably rotated 20 degrees. Or excuse me, 7 degrees. And so we can start matching things up. So this is, again, the one on the right is the 18th, 20th. And I'm basically telling myself this. So we can see those two spots, this sort of line of spots, this sort of line of spots. And then the big one is this sort of Y feature of sunspots. You got this over here. You got this over there. You got that little one. You got that. I don't know if you can see that very well, but there seems to be a spot there as well. And so now this one, I don't see where that went to. Oh, maybe there, but that's a guess. We could take these two images and then we can compare the two, and we can see essentially from pixel positions what the distance these spots have traveled over 2 days. And from there, you can ultimately get a rotation. But there are other things to throw in. Again, these are all very half-formed at this point. It really only occurred to me today is that what we're looking at a curved surface, presumably. Again, science tells us that the Earth the Sun is a sphere. Well, first, let me talk about kind of the elephant in the room, in that I talked about these two spots, this line of spots, and this line of spots. I didn't talk about the specific spots themselves because you can see this structure changes. This is anticipated. Sunspots, and more specifically sunspot groups, where you have a spot in a group or a cluster of spots, that is not expected to be stable on any more than, like, individual little spots in that group are not expected to be stable for any real length of time. So over the course of 2 days, it is very well expected that individual little spots are going to come and go. But the overall structure of the spots is going to somewhat remain the same. And these structures, they are fairly long lasting. They can last days, usually weeks, even maybe a month. You might be able to see one of these structures come all the way back around. So when we do this, if we were to do this analysis, if we were to try to determine the rotation rate of the sun based on spots, one of the things that we're going to have to be very careful about is identifying like spots. Like, for instance, if I were to do this, then I would choose that spot and that spot as being analogous. That spot and that spot being analogous. This one and that one, so forth and so on. I would probably choose localized spots rather than any particular spot in a particular group, unless it is very prominent. But it's a curved surface. So naively, what you would do is you would say, oh, all right, I know what the XY position is here. I know what the XY position is there. I know the exact time between these two images. Let's say it was exactly 2 days. I have distance, I have time, I have velocity. If I've got velocity, then I can determine a period. But the problem with that is if you just naively do that, if you just naively do XY positions, then you are ignoring the fact that the sun is curved. And so it's going to change things like due to foreshortening. Like, for example, if you look at these two spots, I'm not going to do the measurements because I don't want to keep you all here. These two spots, they look distinctly closer here on the 18th than they do here on the 20th. Again, I would have to take measurements to be absolutely certain. But that movement, that change in distance, that is due to the foreshortening of the sun. Now, is it also due to this change in essentially the magnetic field, the what's going on locally. Yes, that is also true. But again, this is why we don't just take one measurement and then call it a day. I would need to determine, I would take multiple measurements of multiple spots over multiple cycles in order to be able to say anything confidently about what the rotation of the sun is. Now, there's another conflating variable. And so, again, this is what science is. This is what, when science is done, one of the major things that we need to consider are conflating variables. What is going on that would hinder our analysis or cause complications? CC is a alt-az telescope, meaning that it moves in altitude and azimuth, as opposed to an equatorial telescope that moves in right ascension and declination. If you're in right ascension and declination, when you take a picture of the night sky, that's what that night sky looks like, with a possible flip due to the optics involved. With an alt-az telescope, you have another complication, which is known as field rotation. So now let's take a look at April 16th and April 18th. These two observations, I am going to bet were not taken at the same time during the day. But if you bear with me, let's look at, say, these two, this thing, this over here. I would argue that what we're looking at is this grouping over here is this spot is that spot, and that these are these. So obviously, the sun is going to rotate in one direction and one direction only. But because of field rotation, we cannot say that rotation is going to always be from left to right, or from along this line, or from another line. This is actually rotated in this direction relative to any other observation taken, unless the times match, unless the altitude and azimuth match on subsequent days. There's going to be rotation with respect to one or the other. Because you can think of it as, imagine you're looking at an object on the horizon, and it's going above the horizon and then down the horizon. So if you're looking at the sky, think about you're looking south. If you are looking over here at this thing over here, this is south going to north around you. If it's here, then this is south and this is north going around you. The southern lines all converge at the bottom. The lines of up down, if you want, for lack of a better technical term, all converge in the south and all converge in the north. So as you look at this thing, if you're just looking at it from an altitude and azimuth perspective, this thing is going to rotate as a function of its location on the sky. Now, right ascension and declination, since the sun is traveling basically is fixed in right ascension and declination, the telescope itself rotates as it tracks the telescope, or the telescope itself rotates as it tracks the object. So you don't have this field rotation. So you can, in fact, compare apples to apples. So now I put it upon myself to try to figure out a way. Either I'm going to look up what the relationship is, which is probably what I'm going to do. And I'm going to correct all of these images because, again, going back to my sexy spreadsheet, I have recorded what the altitude and azimuth is for each of these objects. So there should be, I'm fairly confident there's a way for me to take these alt as observations and then correct for field rotation. So yeah, so I'm hoping that I can actually show at some point I could correct them and I actually can create a time lapse or GIF or something of watching the sun rotate. That's actually one of my one of the goals that I have in mind. Yeah, what else was there? Okay, now that is what's going on there. Now, I've never done this, so you have to bear with me. I'm going to try to share my screen on the iPhone with my MacBook. Because I want to show you this thing. Oh, user tip. I don't care about your user tip. Here's the welcome screen. Globe Earth versus Flat Earth debate. 2/23/24. InfoWars banned video. Uncover the truth between Harrison Smith and our friend Austin Whitsitt. So that pops up. Apparently, I've never seen this specifically, but I guess it gives you upcoming debates on the pop-up screen. So yeah, that's cool, I guess. So let me look up real quick how share. Yes, that's they're both open control center. I'll do it on this side. Control center. No, that's system settings. Control center. There we go. Okay. Got that up. Tap the screen mirroring button. Oh, all right. Probably should do it over here. Probably be doing that on this thing. Settings. Control center. Access with apps. Screen recording. Sorry. All right, collect your voice. Yeah, find the video that you want to stream. Nope, don't want to do that. I want to stream video. Stream video automatically. Don't care. Mirror your phone. Okay. Let's see. Beep. Beep. Okay. Something happened. Okay. I think I'm going to have to do something here. Yes. Yeah. All right. This is on the wrong thing to do. I think I'm going to get this. I think I can. All right. Let's do that. Can I tech? Okay. Haha. Nope, that's why is this not working? That's not working. What? What? Let me do that. Let me do that. Inception. I know this is exciting entertainment, or exciting entertainment. I probably tested. I probably should have tested this. All right, now it doesn't even want to do it. How about now? Okay, you guys are just going to have to deal with me holding it up to the screen. I will figure out how to do this later. Yes, there we go. All right. Yeah. Can't do it. Whatever. All right. So we got that. Like I said, you got, the debates coming up. And then you've got, here is DIRTH's Flat Earth Thingy his Flat Earth app, which technically, or which shows you, all right. So you got the axisymmetric yada yada, the Flat Earth map, whatever the hell the damn thing's called, the Gleason map. You got the North Pole in the center. You got Antarctica, the ice wall on the sides. You got the sun is over here. You got the moon over there, and they circle around the North Pole. And so right now, it's 7:17 where I am currently, and so the sun, it would be directly over the Pacific Ocean, and the moon is now directly over, what is that? East Africa. Ta-da! My first thing that I noticed was that if I see a dial like this, I want to play with it. I want to move it. I want to be able to touch it and then change it to wherever I want to go. Basically, I want to set the time to whenever. I want to see what this thing is what the Earth, Sun, Moon look like a day ago, 5 days ago, what it's going to look like in 10 days, that sort of thing. I want to be able to touch it and move it around, because in other apps that I have that are similar to this, not Flat Earth, but are similar to, like, daytime, nighttime, looking at the phase of the moon, you could always physically manipulate it that way. You can't with this. I was talking with Ollie this last night, and Ollie, I cannot pronounce your last name, so I'm not going to say what it is. It starts with an H. If you have not subscribed to his channel, I know I'm not giving you a whole lot of information, but sub to his channel. He's an awesome dude, makes awesome content. Well, he wanted to know, he wanted me to test, to give him a screenshot of what the flat Earth model would look like during sunrise of in San Diego on a certain day. And so the only way that we figured out how to do it was to actually change the time in my phone to the specific time that he wanted, and then the app updated. So there's that. But you can, in fact, actually figure out what's going on in the future. Down here in the bottom right for me, it's a little bunny, and you can set it to, really fast, marginally fast, and then real time. Cool, I guess. I haven't looked at that enough to see whether or not because again, according to the flat Earth model, or at least this particular version of the flat Earth model, seasons are caused by the sun moving out and in. I haven't really had a chance to actually play with this to see if the sun and moon, or at least the sun, its position across the disk from Capricorn to Cancer actually does change. The lines, the tropics of Capricorn and Cancer are actually shown, so I'm assuming they are. Let's see here. Yeah, super fast isn't super fast. It's a day every 10 seconds, something like that. So I'll play with that later. But what I found to be really, really cool, all right, was if you look over here, if you look right there, I know you can't see it, but that shows what the phase of the moon is in presumably percentage of illumination. It currently says that it is anywhere between 92% and 100%. That seems like a big flaw to me, that this thing cannot tell you what the phase of the moon is right now. What percentage of the moon is, in fact, visible right now? I can Google it. Let's see. Lunar phase right now. Right now, it is 97% illuminated, according to space.com. So, yeah, I guess that falls within 92% to 100%. Seems like a big range to me. 8% is, nearly, you can't tell the precision or you can't tell the phase of the moon to any better than really 10%. I can tell you that I did look at this not maybe yesterday or the day before, and it was the range that was listed wasn't right. The moon was actually more illuminated than even the upper end of the range. I think the only reason why this is correct is because it can't go any higher than 100%. So yeah, I see that as a problem. Why is it that this app cannot tell me what the phase of the moon is any better than 8%? It tells me the rising and setting times of the sun. Let's see if that's accurate. It tells me that today the sun rose at 6:22 a.m. and then set or is going to set at 7:52 p.m. Sunrise, sunset. So, according to the Googles, sunrise is at 6:21 and sunset is at 7:54. Now, obviously, that is going to depend on your location. So, the app, from my understanding, is in fact using the GPS, which is irony in and upon itself, a flat Earth map using GPS to figure out where it's located. But it is using GPS of my phone to figure out where its location is. Dave, if you watch this or recommended this, anyway, if you watch this at some point and I'm getting this wrong, please feel free to correct me. I am not intentionally trying to strawman anyone. But from my understanding, the app is using my location to determine, well, the app is using my GPS to determine that my location. Although, let's put a pin in that for a second, because I'm going to save the really fun bit until the end, and that's related. But anyway, this is basically a couple minutes off. So it's a minute off in sunset or sunrise, and then 2 minutes off in sunset, or at least they're discrepant. Why? Ultimately, what this gets to is, how is this app figuring this out? Where is this data coming from? Is this data being pulled from a website or some kind of service? Or is there actually a mathematical model within here which is actually calculating what the rise and set time are? I would very much like to know that. because right now it's the moon is you can't figure out the illumination of the moon very well, and the rise and set time are a couple minutes off, which to everyday life, who cares? A minute here, a minute there. I mean, we're also talking about, oh no, this is a physical sunrise and sunset. So, I mean, yeah, everyday life, who cares? Minute here, minute there, whatever. But I mean, if we're going to get into the nitty gritties of comparing the accuracies of models, minutes are important. Also, according to, and I think this is accurate for DIRTH, I've actually heard him say this or seen this on his screens, is that the sun comes into view. It doesn't rise or set. So this rise or set time, how is that even defined on a flat Earth map? I mean, this is literally a flat Earth map. This is a flat Earth app model. So how is that defined? How do you define rise and set when on your map it doesn't rise or set? I mean, obviously you would define it as when you could see it, but I would really kind of like to know, by what criteria are you measure, like, how do you know you can see it? Because at this point, that would depend on its distance and its inherent brightness. Assuming that you ignore things like haze and all that kind of good stuff, the time at which you could see it is going to depend on the luminosity of the sun and the distance of the sun to the observer. So how do you know so how are you getting the luminosity? How is this being calculated? I needs to know. I paid $2.99 for this app. Big money. I need to know these things. So yeah, this is $2.99. Now, what I find what's interesting is it shows me what the weather is, and unfortunately, there's a lock button or a lock icon, so I can't really see everything there. But if I click on it, mm, mm, I don't think you can see that. Maybe full detailed weather forecasts require the FE Clock yearly subscription, which unlocks all app features. Now, if I go to subscribe, the year plan is $11 a year, which, okay, seems reasonable for an app. I mean, I've seen apps want to charge me more for services. So aside from the whole flat Earth, globe Earth debate, just from app economy, that's not a big ask. I don't think is $11, but I'm not going to pay it, or at least not now, because I'm not that curious. It does show me I can see that the lock button is basically telling me that I haven't paid the yearly subscription, and so I can't see. But it shows me two temperatures, 17 degrees and 14 degrees, presumably a high and a low. From my understanding, DIRTH's an American. We don't use them. That would mean that it is freezing. And while I am kind of overdressed for the temperature, it's certainly not anywhere close to 17 degrees Fahrenheit here. So that's got to be Celsius. I can tell you that the temperature today ranges from around 40 degrees Fahrenheit to about 63 degrees Fahrenheit. So if somebody wanted to check the conversion on that to see if the high-low even makes sense, feel free to do that. Now let's talk about all these little buttons over here, because all of these little circles, those are all buttons. So first one, the magnifying glass, is search flat Earth videos, which I cannot do because it's behind a paywall. All right, fair enough. That pops up. The welcome screen pops up again. So apparently the handshake is customize your find a friend. Get a customized referral code. When I tap on this, it wants me to go to YouTube. I don't think I will. Oops, cancel. Let's don't. Yeah. Nope. All right, go away. Uh-huh. Oh no, no, sorry, that was. Uh, all right, I'll show it to you. This is the bit that I find to be creepy and fun. Here you go. Here's a map of everyone who has this app currently turned on. This is their location. For me, you can't see it very well, and I'm not going to try to show it to you with any sort of any better than this. But me, I have a really large circle because it is an approximate location. It's not using my exact location, but I can click on one of these dots. So this dude over here in Springfield, that dude's name is Eric, apparently. This person over here in La Plata, they're Hamster. Emma Elizabeth lives near DC, apparently, or is currently at or in DC. There are two little icons. One looks like a chat bubble. One looks like personal information. They're locked. So I'm assuming that if I paid the $11, then I could chat with Emma, and I could know more about Emma, or at least as much information as she put into here. So yeah, it's a locator app. Stephanie, that is correct. Good, bad, or ugly. That's what this is. That's one of the features of it, which I can understand. If you're in a community that is marginalized, knowing where others in your community are can be helpful. Now, did I know that was going to be in the app when I downloaded it and got it in? No, I didn't. But there again, I didn't really investigate the app. I just kind of found it and downloaded it. It did, terms of service were there, and I of course did what everyone does and just say, "Yep, agree." So that was a bit of a shock. Like, okay, I'm not a real big privacy buff, as you might know. I am very open about who I am, where I work. Obviously, I'm going to draw the line at my mother's maiden name and birthday and all that kind of, or birthday and social security number and all that kind of good jazz. But I'm not a huge, like, this doesn't bother me, but I can see how others may be kind of weirded out that others could find you on this. If you hit the star with, has a star icon with a FE on it, you get a list of people, like Matthew on X. You click on it, you get that. So I'm assuming these are, and if you click on it again, it actually sends you to the page. Let's see. Let's get triggered. The Earth is flat, still flat. I click on it, and boom, takes me to his page, or takes me to his TikTok, their TikTok, whoever. Cool, I guess. Again, connects you with people who believe the same thing you do. This welcome string keeps popping up. He really wants to let me know that Witsit is going to be debating somebody. Web, a little web icon brings me to this stuff, which is video by DIRTH, all videos, interviews, presumably by DIRTH, Flat Earth for Kids. Got to click on that. Okay, opening that up. Okay. This is Flat Earth Dave archive. Do not sub. It's got the first video of some Black Puppet and Elmo. There is Kiko and Agzuamwan something. Earth is flat. Just a Globe, FE Kids. Kakalaki Crew and BK Superflat. Again, puppets. I don't know what kind of, I really don't know what kind of fever dream I've just fallen into. This is kind of disturbing. It looks like there is Cookie Monster wrap, Flat Earth. I don't know how I feel about that. Monster and a brown Elmo. Yeah. All right. Anyway, I'm gonna. So there's that. So that there is. Yeah, I know. Stop that. Books. It actually gives literature, which I appreciate. I'm a book guy. I like books. Hidden Lands Beyond the Antarctica. Don't know the author. John Levy's Old World. Do we live on a planet? Answer that is yes. Biblical Cosmology, a study guide. Level Plane Poem 4. 16 emergency landings proving flat Earth. Flat Earth FAQ. I doubt that's a book. All right. Maybe it is. Who knows? Biblical Cosmology. Flat Level Plane Poems 2. Cooking Up Conspiracy. Okay. So yeah, we got some books. That's cool. Go away. What's the flag? Okay, so there's a flag icon, which brings me to this. The one that looks like it's in Cyrillic actually has a picture of Elon Musk wearing a crown. Will not, in fact, be pushing on that. There's a Hebrew one. Netherlands. What could go wrong? Let's click on the Netherlands. Let's see what the Dutch have to say. This is Flat Earth for Nederlanders. So, Flat Earth NL, and a whole bunch of stuff that looks like Flat Earth, but it's not in a language some of it's in a language I can read, others not so much. So I'm guessing this is Flat Earth videos from around the disc, the globe. I don't know. Now I'm being silly. Let's see what else we got here. We've got this thing, which if I cared more, I would figure out what this is supposed to do. But it's a little thing that switches on an added clock thingy do, where the hour hand is pointing. It's pointing at, now we have another sun icon that says 12. I guess that's supposed to be noon. And then you have on the back end, you've got 12 with the moon. I don't know. Like I said, somebody can figure that out. I don't know. I didn't want to spend too many brain cells on it. It's got probably the thing. It still makes me laugh. It's a compass. North is in the center. South is all over the place. And it moves. Yeah. So south. Yeah. That's still south. Also south. So yeah, I think I'm doing this wrong. I think I'm using this wrong. All right. Ooh, shows you what the zodiacal signs are. I can see it doesn't include Ophiuchus. Bigots. It's a time jump. There's a little icon of a dude kind of going wee. Apparently, if you click that, it makes the thing jump. Yeah. What is it? A day at a time? Yeah, a day at a time. I don't know how to get back. How do I get back? Okay, now I'm stuck on. Oh no, it got back. All right, cool. This thing, Rofkin YouTube. So gives longitude and latitude and meters per second. Oh, data. It's wind. Ooh. Oh, hold on. This I'll play with later. Darn it. Can't I? Ah, there we go. Magnetic flux. Ooh, that looks pretty. So right there, the magnetic field strength is 17,286 nanoteslas. Come on, we have scientific notation for a reason. Yeah, there's no reason why that needs to be a nano Tesla. Just give it to me in scientific notation, baby. So that's cool. So yeah, you can do magnetic field, winds, oceans, clouds. I don't know who Rofkin YouTube is. I'm assuming that's where this is coming from. Projection is azimuthal or equidistant. So that is clouds, I'm guessing. Let me see, but it won't change from azimuthal to equidistant. So let me go back to wind. Equidistant. Ah, there we go. There is wind on a globe. So I find that to be interesting that the app says that the flat Earth is a projection, and he refers to, how does he refer to it? The globe is equidistant. Okay, I don't know. Oh, you can change the heights, so that's actually kind of fun to play with. There is, and this is the only thing that shows up in. Oops. This is the only thing that shows up in portrait. Everything else you are stuck with landscape. It doesn't auto rotate. This is the only thing that actually gets into portrait. Don't know why, but it is the user referral leaderboard. So you can, I guess you can win fame and prizes. So we have KCD Industry has referred 2,786 people. DIRTH, man, this is your product. You've only referred 122 people. I think you need to get on that, buddy. Let's see who else. Karen B, 30 people. Rakia, I know who that person is, 24. Oh, apparently there is someone called Level Plane Poem. That's 24. Jeranism, 15. Hibbler Productions has referred people 12 times. Troubling Tribune, 9. I'm just stating people that I recognize them. Flat Smacker Mike, no idea who that is. Robot Polisher. And that's it. So yeah, you get a nice leaderboard to show you how well you've been hawking his website or his thing you do. And then the last one is game. Flat Earth Truth or memory something or other, which is in development. Again, these are behind a paywall. So, and it also has a featured video down here. So, what are my thoughts? It's $2.99. Okay. I have there are other apps like Sun Clock and Phases of the Moon, other astronomy apps that I've used that are somewhat comparable to this in a way. Those are free, although this does have a lot more little features. Specifically the locator to find people, the recommendation of books, the recommendation of videos, assuming that those are actually updated. Is it worth the $2.99? Yeah, I mean, sure. I don't feel ripped off by doing this. I don't. What I mean to say is, from the amount of content that I'm receiving from this app, I do not feel that I was ripped off by paying a one-time fee of $2.99. Now, that being said, you really got to improve that moon phase indicator, because, like I said, it's telling me that the moon is anywhere between 92 to 100% full, meaning that I'm guessing, I don't know if that means that it's depending on your location, because again, given this geometry, it should. If that's what he means, or if it's because of just simply the precision of, or the accuracy rather, of whatever it is that's giving me this value of 92 to 100. I just I don't know. Which gets into the major thing. The major question that I have for this is, how does it do it? How does this app give me the rising and set times of the sun? What does that even mean on this geometry, in this geometry? How does it determine what the phase of the moon is? How does it determine where the sun and the earth are on this dial? Things of that nature. Oh, it does have a cool little countdown timer. So you could set it for a time and date, and it will give you a countdown timer for reasons. Not entirely, I don't know why. If I had figured this, if I had gotten this before the eclipse, I would have, obviously set it for the eclipse. But yeah. And again, there are a couple of features that I don't have. I cannot, for the location finder, the people that are around me who have this app, I can't know anything about them, just simply their username, unless I give unless I pay the $11 per month. Again, $10.99. Why not $9.99? That bugs me. I don't know why. Subscription service, yearly or a monthly. No, it's yearly. Sorry, it's yearly. Pay $11 a year. You can get that information. It gives you a weather forecast if you do that. Hopefully not in Celsius, because I'm an American. And it shows me an icon of that would indicate that it's partly cloudy. It is not. It is actually pretty clear. So that's not right. But yeah, there you go. That's basically that is my assessment of DIRTH's Flat Earth app. I will let you know if I discover that my phone has been hacked, or if my phone gets malware or any of that stuff. I will certainly let you know, because none of that has ever happened to me in the over decade plus of owning a phone. So if my phone gets hacked or gets malware after I upload this particular app, not saying it will, not saying that it will, but if it does, I'm going to blame that. I'm going to blame DIRTH. So we'll see how that goes. Climate already has malware. Well, it depends on how your definition of things goes, but all right. So, wow, I've been going for about 2 hours now. Let's see. Let's check the chat. Let's see. So it looks to be folks are chatting with Stephanie. Stephanie, I just saw Jupiter on eclipse day. Trillion, howdy. I don't know if I've seen you around. You like turtles. I'm cool. I went on a date with somebody who really liked turtles. Yeah, wasn't a great date. Hey, random crank, answer the questions. Grumpy old mechanic. Check Stellarium. I love that it shows us the dome. It does, Stephanie. It does not show you a dome. It shows you a coordinate system that is overlaid onto a sphere. The only reason, so actually, let's do that. Let us have a little bit of. I feel like staying on. And also I was using Stellarium for the project. So let us. Let's show what it does. All right. Presents. Share screen. Entire screen. All right. So this is Stellarium. If you don't know what Stellarium is, I'm so wokey. Wow, the moon looks super full last night. So bright. Is it the full moon? Oh, it's 97% right now. So technically no. Half a sphere equals a dome? Not really. I mean, yes, but not in the way that flat Earth means it. A dome is a dome. Like, I mean, it is anchored to this. Well, maybe I'm putting words in people's mouths, but from my understanding of the dome, that means that it has to be anchored somewhere. At some point, you should be able to travel to where the dome and the Earth connect. I don't know where that is. I don't know if anyone has ever specified where that is, but so yeah, let me address the malware issue. Yes, am I a little bit am I laissez-faire in terms of installing malware and all that onto my phone? Probably. Well, no. The answer to that question is yes. I am laissez-faire when it comes to that. I didn't really. It did not even occur to me that DIRTH would be giving me malware. I suppose that was my faith in the system, that if the app was in fact harmful, that at this point it had been out there for so long, somebody would have reported it if it was in fact harmful. In terms of the location information, like I said, it doesn't use my precise location, and for better or for worse, I am not a huge privacy nerd. Not nerd. That's not what I mean. I do not. I'm not a huge stickler on my own privacy. If someone wants to know where, obviously they know my name, they know where I work, they can easily find where I am most of the day on weekdays. So, yeah, that ship has already kind of sailed. So, but I fully understand why others would not want to do that, and that's one of the reasons why I put that out there. Is it is a locator app. It will show your location, proximate or not, to others who have this app. So if you are thinking of getting the app for whatever reason, please be aware that that's going to happen. Parks, that is the imaginary construct called the celestial sphere, and it uses a mean sun, not the actual sun. Does it? Does it use a mean sun? Why is my computer? Okay, well, apparently, I think I don't even know if I'm still online. Chrome seems to be giving me the wheel of death. And I think I'm stuck. So, All right. Well, there's one way to do this. Is it because of this? I wonder if it's because I have so little RAM. No. All right. Let me see if I am still online. Oh, did it come back? I think I'm back. Nope. Nope. Something's happening, I think. You. Something's happening. Yep. So I'm still online. You guys are still seeing me, but Streamlabs or StreamYards is frozen. So I will have to look at the chat through here. So yeah. Audio 5x5, video froze. Yeah. I'm pretty much I think this is God telling me to stop doing this and